Okay, let's start with this topic of CO4. And this CO4 is about set theory, elementary number theory, and discrete probability. I have made this set theory underlined because we have already seen something related to sets. So we will not touch it again. These are the COs available in the curriculum. Some person designed and then nobody have changed or modified those things. So that's why this is the word again. Anyhow, so we will focus more on number theory and discrete probability. Number theory, you have seen the integers and you can perform different operations on these integers. Either these integers are given to you into the form of a sets or series. You can do addition, multiplication, division, subtraction, and many other operations. So in mathematics, the study of the set of integers and their operation properties is basically called number theory. And the topic on which we will focus in this lecture is the divisibility and the modular arithmetic. The divisibility is about division. Modular arithmetic is about modulus, which is again a form of a remainder. And then we will see integer representations, how you can represent an integer into a binary form, octal form, decimal, hexadecimal, whatever. We will not go into that much detail. We will see them only algorithmically. And then we will see some primes, what is prime number, and we will see some theorems and prime numbers and some examples in this discrete mathematics. And then we will see GCD, which is the greatest common divisor. And there is also another topic, least common multiple, like that, LCM. So we will see these GCD and LCM there in this topic. And finally, we will see the congruences. That would be, maybe it would be a new thing for you. In all the topics, the beginning definition would be, you would be familiar with the beginning definition, and then you will see some additions in those fundamental concepts that would be different from your existing knowledge. There is another topic that is called cryptology, but I removed that topic from here because according to the statement of CO, I have this option to remove things from there. The other thing is that I want to complete this course within that 11 weeks time period. So that's why I have just skipped that topic from here. Otherwise, that is also like these topics, that topic is also an important topic in which you normally see how you can encrypt a message and how you can decrypt a message, how you can encode things and how you can decode things. So there is one or two algorithms given there, and those algorithms will take some message, it will then decrypt them. I don't know what was that subject, maybe AI or whatever. I have this cryptology somewhere in the slides of artificial intelligence. Anyhow, That is an important topic, but what I can do, I don't have any option. So, number theory, what is the use of number theory? We use these concepts in computer and internet security. This is the general term. In computers and internet security, we use these concepts. And these are some examples when normally a machine produces random numbers, pseudo random numbers. So there you are using number theory. Assigning computer, when your machine is assigning memory locations to files. So there you are using number theory, and there are many other examples. At etc you can say. So let's start with this topic, and the first topic and the first section. According to the textbook, the first section is 4.1, and now it is divisibility and modular arithmetic. So now here we have the definition for the division, simple division. Division is an operation in mathematics, and what is the definition for it? So that is simple. So if you have two integers a and b, and if a not equal to 0, this first one is not equal to 0, it means that it is a positive, it is 1, 2, 3 or greater than 0, not equal to 0, then we can say that a will divide this b, a will divide this b, and when it will divide, you will get some quotient, that would be integer c, and if that would be integer c, then you will have this equation for this division. B is equal to AC. B is a number that you are going to divide. A is the divisor of that B, which is dividend, and C is the quotient, which is here multiplying with this AC. So divisor and the quotient, but the value of this multiplication would be equal to this B. Or equivalently, you can also say that A divides this B, and when it will divide, you will get some result that would be an integer. That would be an integer. Okay, so this is the normal definition of division, no issue. And in this division, when you normally say A divides B, then this A is called the divisor or called the factor, and then B is called the multiple of A. And how you can represent this division? A divides B in mathematics, in discrete mathematics. A, this parallel, perpendicular pipeline, you can say, A divides B. This is not A or B. This is A divides B. And also this does not mean that B is dividing A. No. Here it is meaning that A is dividing B. This is only confusion. There is only this one confusion from our general practice of mathematics. If it is a mathematics, we normally say that B is dividing this A. No. Here, A is dividing this B. But if you have this symbol like that, then you can say, okay, B and then A is here. Here, A is dividing B, okay? But if you have this symbol in discrete math, then we normally take it as A divides B. And when something is not dividing with B, then you can write A not dividing B. Okay, this is the definition of the simple division. And in the next slide, you will see some additional concept based on this fundamental definition. That would be with the passage of time, those would be new concepts for you. But this one is you are already familiar with. And there is a theorem 1, and you will see many theorem statement in this lecture. And it is your duty to memorize and understand those statements of the theorem. So here we have the theorem 1 with respect to this division. And this theorem is saying that if you have three numbers A, B, and C, and this number A is not equal to 0, then this is also true, this is also true, this is also true. And what this is, for example, number one, if you have three numbers A, B, C, if you have three integers and A is not equal to 0, then these all three statements are true. And these statements are proved already. You don't have to prove them, you only have to memorize them, because it will give you the understanding for the next questions that you have to solve. And here it is being said that if A is dividing some number B and A is also dividing some another number C, if A is dividing B individually and C individually, then A can also divide the addition of these two numbers. Okay, so B plus C is what? B plus C is that simply addition of those two numbers to whom this A is dividing already. So whatever the addition of those numbers, A can also divide that addition. So now you have the understanding. If there are three numbers, A is dividing B and A is also dividing C, then what you have to do? You can add B and C, and whatever the sum you have, that would be divisible by that A also, because A is already dividing B and C. So this is true. And then this second statement, if A divides B, then A can also divide B, C, and C is any integer. Any integer. Okay, no issue, because this B, which is now the part of this product, this B, which is now the part of this product, is a separate entity here when A was dividing it. So now as this B is the part, so A can have that ability to divide that B portion. But overall, for example, that number is 700 and the B was maybe 100. So 100 is a part of 700. So by taking that property, you can understand that if A divides B, then A can also divide B and C. And that C is what? An integer, which is multiplying with this B, and you are getting some 700. And if B was 100, then you can understand 100 is the part of 700. So anyhow, so this is also true. Now the third statement is saying that if A divides B, and then this B is dividing this C, there is a sequence. If A is dividing B, and this B is again is dividing C, then you can say that this A can also have the tendency to divide this C. A is dividing B. Okay, you only have to keep these statements in your mind. So if this B is a number, A have the tendency to divide it. So B is divisible by A. And B, which is divisible by A, can divide some other number. Can divide some other number C. Then it means that there is some divisibility property existing all these three numbers, A, B, and C. They can divide each other like that. So by taking that property, we can say A can divide this C. Anyhow, now we have another theorem for this division. For this theorem, we have finally this equation. A is equal to dq plus r. A is equal to dq plus r. Here, for example, A is simply an integer and D is a positive integer. When I say positive integer, it means 0, 1 is 1, 2, 3, 4, not negative. A is simply a number and D is a positive number. And when you will divide this A with this d, which d is for divisor, you can say. When you will divide this a with this d, you will get some quotient and also some remainder. And that would be the form a is equal to dq, divisor multiplied with the quotient, you will have something. And if it is not dividing completely, then you will have some remainder also. That remainder can be 0 or can be a positive number, which is written here. Remainder greater than or equal to 0 and less than this d. D is a divisor. D is a divisor. Understood? So this equation is again the equation, the concept, you already know that. And we can understand this with this example 1. For example, what are the quotient and remainder when minus 11 is divided by 3? What is so when minus 11 is divided by 3, what is the quotient and remainder? What is the value here? Quotient. And what is the value here? Remainder. This question is asking simply that question, third, fourth class question. But if this would be not mentioned here, then it would be an issue for you. Little bit confusion. But it is mentioned there, so now you are saying it's easy. Anyhow, so if it would be 3, 4, and 12, then if it is a positive, then you can make it negative, and then you have the answer like that. Or the other way is, there is a rule here, remainder cannot be negative. So here the remainder is becoming negative. So then what? I have to go with minus 4. And then it would become minus 12. And then I will change it to plus due to division. And then what will happen? You will get 1 as a remainder. So now according to that rule, now it's okay. Now it's okay. And then you are getting 1. So here the question is simple, but it can give you a hard time with a little bit trick. So now this is the rule. Remainder cannot be negative. So that's why minus 1 now is equal to 3 multiplied by minus 4. And then plus 1 is the remainder. And then you can say the value is equal to that one. Both sides are equal. Both sides are equal. And in this form, this is A, this is D, this is Q, and this is R, according to that equation. Okay. Now we are moving towards another definition, that is modular arithmetic. That is modular arithmetic. Modular is coming from a word modulus, and modulus normally means something that you will get as a remainder. When you divide some number with some divisor, some modulo value, then you will get the remainder. That that section or that or the concept related to this modulus is called modular arithmetic. And the equation for this definition is something like that. And in this equation, A and B are integers, normal integers, positive, negative, whatever. And then M is a positive integer. M is a positive integer, not negative. And then we can say that A is congruent to B. A is congruent to B modulo M. Normally, congruent means something which is in agreement. So here congruent means A is agreeing with the B modulo M. Or you can say the left hand side is agreeing with the right hand side. But the term here is congruent. Congruent. So A is congruent to B modulo M, or you can simply say mod M. It is up to you. And when this congruence, so you have to find this congruence. In this equation, you have to find this operator, congruence. Left hand side is congruent to right hand side, or you can say A is congruent to B. You have to find when normally A is congruent to B modulo M, if M divides A minus B. If this M, which is a positive integer, if it is dividing A minus B, that's the difference of A minus B, the subtraction, you will subtract them and you will have there some value that is called A minus B. So you can calculate A minus B by putting their numbers, values here into these variables. And then if that M, which would be a number in the question, if that M is dividing this A minus B completely with zero remainder, then finally you can say that this A is congruent to B modulo M. Okay, this is the condition. This is the meaning here. And you can represent that congruence into this equation. A congruent to B mod M. M is what? M is modulus. And when A is not congruent to B modulo M, then how you can represent? With this notation. A congruent, you have to strike it out. A not congruent to B mod M. So this was the definition, and now it's a related theorem, theorem 3. Similarly, we have two integers A and B, and M is a positive integer, as we said earlier in this definition. Then A congruent to B mod M. So this would be, this congruence will hold. What is the condition? If and only if, this is the condition. If and only if we can write A mod M, if A mod M individually, and you will have to calculate the value, is equal to B mod M. You can write A and then mod M, and then you can write B and then mod M. If A mod M equal to B mod M, then you can say that A is congruent to B mod M. So if there would be a question that find this congruence, then you can either use this definition or you can use this definition to find that congruence. We have an example here. And this example is saying, determine whether 17 is congruent to 5 modulo 6. Up to that point, there is one part, and then there is a second part in this question. So determine whether 17 is congruent to 5 modulo 6. No, so now this 17 is A. This 5 is what? B. And this modulo 6. This 6 is what? M. According to that equation. And now you have to find that 17 is congruent to 5 modulo M. It is the case or not? Congruence is holding here or not? Holding means happening here. So how you can find that? Here, then A is congruent to B modulo M if M divides A minus B. This is one condition. You can find congruence by using this concept, or using this concept. It is up to you, or according to theorem. By the way, this is also the same thing, a minus b mod m, if you will simplify it. So m divides a minus b. Okay, then this 17 is, if it is a, if it is b, so 17 minus 5, but what you will get? 12. So this is a minus b, 17 minus 5. You are doing what? A minus b, 12. And then you have to divide it with 6, which is m. It is divisible. 70. So it is divisible. 6 multiplied 2 times, and then you will get 12. It is multiplying completely with 0 remainder. So it is dividing. So then you can write it into this form. 17 congruent to 5 mod m. You can write. So what it means, 17 is congruent to 5 modulo 6. If you have remainder, then it's not. You can see this example here. So this part, now second part is 24 and 14 are congruent modulo 6. Because in the definition we are saying if m divides a minus b. And normal understanding of divides mean completely division. Completely division with 0 remainder. So 24 and 14 are congruent modulo 6. So now this is A, this is B, and this is M. M is the same. So 24 minus 14, you will get what? 10. And 10 is not divisible by 6. You will get some remainder, which is 4. So 24 minus 14, that's why we are writing 14 not congruent to, 24 not congruent to 14 modulo 6. This is easy, but you will see the things like that next with some additional concepts. Now we have another theorem for modular arithmetic. And what is the statement? Statement is, now you know m. What is m? M is a positive integer from our previous knowledge. M is a positive integer. A and B are integers. And we are saying that A or B are congruent modulo m, which means A congruent to B modulo m. That equation that you have seen here, which means this equation, okay? Which means this equation. So this statement, integers A and B are congruent modulo m. What is the equivalent of this statement is this one, this mathematical equation. A congruent to B modulo m. So this theorem is saying that if A is congruent to B modulo m, so this congruence will hold only if this is the situation. This left hand side, these are the reserved word. If you just remember CO1 and CO2, in which you normally change your English statements into mathematical statements. So I am saying that this is the reserved word. There is a left hand side before that, and there is a right hand side. And the left hand side of this theorem statement is saying A congruent to B mod m. And this congruence will hold only if this right hand side holds. If this right hand side holds. And what is this right hand side? Right hand side is saying that there is an integer k, and you can write that integer k in this mathematical equation. A is equal to b plus km. A, b are the two integers that you are using from previous slides. M is also a positive integer. And what is that k? K. And in the previous slides, we are using m for division, but due to this mod, we are getting remainder. But m is something dividing. So here, if m is something dividing, and then something is multiplying with this divisor m. And we are saying A is equal to B plus Km. So maybe this K is some kind of quotient, according to our previous knowledge. According to our previous knowledge. But we will see. We will confirm it here in this proof. It is, by the way, it is a quotient, but it is not mentioned in the theorem statement. So now this theorem statement, what is here in this theorem statement? In this theorem statement, we are saying the left hand side is saying A congruent to B mod M, if and only if, double implication, A is equal to B plus Km. This statement, which is written in English sentences, I have written it into a mathematical form on this whiteboard. On this whiteboard, for your understanding. So now there is a small direct proof, so that's why I mentioned it. Otherwise, I don't want to mention it. Small proof, because there are 7 to 8, or maybe a little bit more. There are different techniques to prove something. Those proving techniques is also the part of this discrete mathematics. But here you have only 11 weeks, so we cannot give you the whole stuff. Otherwise, for example, in CO1 and CO2, there are different proof techniques. For example, maybe you have heard proof by contradiction, proof by contrapositive, proof by negation, proof by counterexample, proof by mathematical induction. There are different techniques. There are different techniques. There should be one chapter on it. And this should be the part of this discrete mathematics. But in the statement of COs that you have for this course, those are general. So if those are general, a teacher can expand the course or shrink the course. And that portion is now shrinked. Okay. So, but anyhow, that portion is also an important portion. But you will see that topic again, I hope, hopefully, maybe in algorithms. Maybe, I'm not sure. Maybe in theory of automata or theory of computation, there is a course, theory of computation. And this portion, proving techniques, is also the part of the first chapter of that theory of computation. I don't know either you will study this course, theory of automata. Theory of automata is a core course for computer science students. But I never ever heard this course here in Islamic University. This is the core course, theory of automata. Anyhow, so here this theorem is saying something like that. So you have to prove, and this theorem is saying that this congruence is true whenever this is true. Whenever this is true. And to prove this theorem, because the proof is simple, so that's why I have just made it the part of that slide. And we are using direct proof technique here to prove that. And what is direct proof? You have to take the left hand side and then you have to argue. You have to present your arguments. You can modify, you can use other definitions. You can modify the statements, and then you have to reach at the right hand side. When you will reach at the right hand side, then again at this point you have to take this right hand side and you have to modify. You can use other existing definitions, and then you have to reach at the left hand side. So in this direct proof, you have to go from the left hand side to the right hand side, and then from right hand side to the left hand side. And in this way, if you will start the left hand side and if you will reach at the right hand side, and in the opposite direction are called conversely, when you will start from the right hand side and you will reach at the left hand side, if it happens, then that thing will be proved. Then that thing will be proved. So here in this proof, we are starting from this left hand side. Integers a and b are congruent modulo m, which is the mathematical equation form of this left hand side is this one, a congruent to b mod m. So this is the left hand side of the theorem statement. So now we are using the definition of congruence. On this equation, we are using the definition of congruence. What is the definition of congruence? This one. A is congruent to B modulo M if M divides A minus B. So this is the definition of this congruence. When there is a congruence between A and B, when M divides A minus B. So we are using this definition. And what this statement is saying, this is saying A congruent to B mod M. So we are using that definition and we are modifying, changing this equation. We can write this into this form, M divides A minus B, by using that definition. Congruence holds when M divides A minus B. And this is a theorem. This is a definition. This is a definition. It means that congruence, when M divides A minus B, it means there is a congruence. So by using that definition, we can write this equation. We can also represent that equation in this way. This equation means that M will divide the difference of A minus B. M divides A minus B. Okay, when M will divide this A minus B, M is the divisor and A minus B, we have to divide it with M. Then it means that this M will multiply with some quotient and then it will be equal to this A minus B. And we are saying that quotient with the name K. And if that quotient, then we can write A minus B, okay, this A minus B, and then we can multiply K and M. This M is the divisor, this K is the quotient. Then if, here again, if M divides A minus B, here we are not mentioning the quotient. We are saying M divides A minus B. If you represent this with some number, this with some number, then you will understand. We have not represented quotient here. And if we say that if K is the quotient, if K is that quotient, an integer, then we can write this equation also into this form. A minus B, which is that side, and M will multiply with K and you will get the value equal to this A minus B. And then you can say A minus B is equal to Km. It's okay or not? Did you get that or not? Why it is confusing? I am recording, so that's why I want to annotate these things as much as, otherwise it's not confusing. A congruent to B mod M. Up to this point, it's clear or not? According to the definition of previous slide, I can say that M divides A minus B. It means that A minus B and M is dividing. If I say that this K is a quotient now, then you will get some value here and then you will have some remainder. This A minus B means some number, maybe 200. So I am saying that this K, if that K, so then I can say that A minus B would be equal to the product of this M and K. Right or not? Which is what I mentioned here. If K is a quotient, then A minus B is equal to Km, okay, or Mk is same thing. And move this minus B to here on the right hand side, then it will become A is equal to B plus Km, this equation, which is that equation. We have started from left hand side and we have reached at the right hand side. There is nothing difficult here. Now we will start from the right hand side and we will reach at the left hand side. So when M divides A minus B, that's okay, but we don't have any. We can say if K is a quotient, which is an integer, then we can represent A minus B is equal to Km. So M is the divisor. A minus B is some value which we will divide with this M, and K is the quotient which is multiplying here. Move this minus B on the right hand side and A is equal to B plus Km. This equation is that equation which is available on the right hand side. So now we started with the left hand side and we have reached at the right hand side. Now what is the step remaining? We have to start from the right hand side and we have to reach at the left hand side. So therefore we are using this word conversely. Conversely means in the opposite direction. And in the opposite direction, we have to start from here, or you can see the statement, we have to start from here, which is the right hand side, and we have to reach here at congruence. Or you can say we have to start from here and we have to reach at this equation. So here, conversely, if there is an integer k, according to that integer k or quotient k, we can write this equation, which is the right hand side, A is equal to B plus Km, which is the right hand side. This is our starting point. So this equation is also equal to A minus B is equal to Km. What is the meaning of this equation? Which is also equal to Km is equal to, if you move B back, then Km is equal to A minus B according to that equation. And what this equation is equal to? That is equation is equal to A divides M minus B. M divides A minus B. So you can write this equation here again, or you can shortly say that what is the meaning of this equation? It means that this M will divide this A minus B. Or you can write it this according to that equation. M will divide this A minus B, and that K is quotient. When M divides A minus B, this is the definition of congruences according to this previous slide. When M divides A minus B, then you can write this equation. When M divides A minus B, then it means this is the congruence between A and B. So when M divides this, so then I can write A is congruent to B mod M, which is the left hand side. So this is the direct proof. This is the direct proof. And now theorem 5. And what is the statement of theorem 5? If M is a positive integer, same M which we are using from the previous slide. And if A, B are two integers, and if there is a situation A congruent to B mod M, if this is one equation, and C congruent to D mod M, if it is another equation, then you can have these congruences also, which is the addition and the multiplication of these two equations, you can say. And what you are doing, a plus c congruent to b plus d and mod m, where it is written, and a plus c congruent to b d mod m, and similarly a multiply with c and b multiply with d and mod m. So you can, so this is a statement of theorem. If you have two equations like that, then you can also convert them directly into this form. You don't have to do any calculation. You can just convert them, and then you can find your results which you want to find. So why I am saying that keep the statements of these theorems in your mind, because it will help you in solving different questions which I have given in these slides as an exercise. Or if you want to solve all the exercise questions which is given in the textbook, you have to keep the statements of these theorems in your mind with the complete understanding. With the complete understanding. Corollary. What is corollary? Corollary is normally a small proof which is basing on an existing fact or proof. By using some existing proof, if you are proving something small, that is called corollary. So this corollary here, whatever it is written it is also a theorem's proofs, you can say. It is also a fact. And in this corollary, we again have m as a positive integer and a, b are simply integers. Then if you have something like that, a plus b mod m, a plus b mod m, addition of two numbers mod m, so that left hand side would be equal to a and then mod m individually plus b mod m individually and then whole mod m. And similarly for multiplication, if you have AB, the multiplication of AB mod M is equal to A mod M, you will get some value. You have to multiply that value with B mod M, you will get some value. You have to multiply them, and then you have to calculate their mod M again. If you have A and B, you have to divide that A with M, you will get some value as a remainder. Here B you will divide it with M and you will get some value as a remainder. You will have to multiply these two remainders and you will get as a result some resultant value. That resultant value you will have to divide it again with M and then you will get something finally that would be the answer of this thing. We are now moving slowly to our relevant questions. And here on this slide, if we have a set Z, if we have a set Z, and what is that Z set according to our previous annotation? Integers. Set of integers. Z is for integers. Set of integers. We have this things represented on some slide in the previous lecture. So Z is a set of integers. But there is a condition here. Some M is linked with it. So this Z is a set of integers, but non-negative integers. Non-negative means positive integers. Less than M. So whatever the M here you have, so this Z will contain numbers less than this M. What it means? It means it will start from 0 because it is positive. So there's no negative numbers, 0, 1 and up to m minus 1. It will have elements like that. If you have this set Zm, then you can define two operations on them. One is called addition, other is called multiplication. For addition, you can represent that addition with this symbol, plus m. Plus m. Arithmetic modulo m. You are going to represent arithmetic operations for modulo m. And now we are going to see the addition, plus m. When you have plus m, you can understand that this m is a modulo m, and you are going to see the arithmetic operation. What is that arithmetic operation? Addition. So you can apply this symbol between these two. You can add any two elements of this set. If a and b are two elements, then you can apply plus m, the operator. This is the operator. And how we can perform this addition? This is right hand side will let you know. Right hand side is giving you the information that you have to add this a and b first. First you have to add those two numbers and you will get some resultant value. That resultant value you will have to divide it with this m, because it is more modulo. So you have to get the remainder and not the quotient. And whatever the remainder you will get, that would be the final result of this addition. That would be the final result of this addition. So this is not a simple addition that you have in mathematics. This is different. And for multiplication, you can use this symbol dot m, and a dot mb if you have two integers. Dot m means you have to do the multiplication with m modulo m. So how you can calculate this multiplication? You can understand it by looking at the right hand side. So first you have to multiply simply a and b together, simply that you normally multiply in mathematics. Whatever the result that you will have, you have to divide it with m and you will have to focus on the remainder. That will be your multiplication result. For example, we have the example 7 here. So use the definition of addition and multiplication. In Zm, there is no need to present the whole set. Z means Z of positive set of positive integers. And M is needed, and the other A, B and also needed. So use the definition of addition and multiplication in Zm to find this one and that one. This plus 11 is that plus m, and this dot 11 is that dot m. And then you have the, how you can do that? By looking at the right hand side, you can find them. So here you have 7 plus 9 AB. So add them, 16, and divided with 11. So as you can see, using the definition of here, these we have the definition of the addition and multiplication. So we can represent 7 plus 11 plus 11. This is a operator. This 11 is the m. So 7 plus 11, 9 is equal to, I can write it like the right hand side of this equation. So 7 plus 9, I can write 7 plus 9 mod 11. This will become 16, 9, 7, 16 mod 11. And when you will divide, you will get 7. So this is the result of the addition. 7.11, 9. Okay. According to the right hand side, 7.9 mod 11. This would become 63 divided with 11, and what is the remainder? This one. This is the result for multiplication. So it's easy. And these are the some questions that you will have to do, because in the midterm, I will give you only the mathematical questions. I will not ask the definitions. That's okay? So you have to focus on the examples and all. Huh? Not now. It is midterm would be up to CO3, CO1, CO2, and 3. Chapter 4. We can include, it's up to you. Okay. So these exercises, you should have to focus on them. The solutions are available everywhere on the internet. You just have to find them and keep it in your record for your final preparation for your mid and final. Take a 5 or 10 minutes break, and then I will start it from here. Some students already are taking breaks. Huh? Okay. Let's start with this second section of the chapter, which is about integer representation and algorithms. Because if we just go into there, divisibility and modular arithmetic, then second is integer representation and algorithms. So here integer representation into the form of binary, octal, decimal, hexadecimal, whatever. You can represent simply an integer into these forms. And there are algorithms. So the use of this integer representation is very much clear, because we know that we have a representation of integers into the form of binary, into the form of octal. If some number will be given to you, and if I will ask to convert it into binary, then you know that there is a base system. So 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3. So this is something for binary. And for octal, how many? For binary, you have 2 digits. For octal, you have 8 digits. So 8 raised power something. And similarly for decimal, hexadecimal, etc. So you can also convert one system into another system. And these are the things that you have seen in other subjects. This is not the main motive of this course, to give how we can convert. This is not the main objective of this course. Maybe in introduction to computers in your first semester, maybe you have studied these things. So theorem, now the theorem statement regarding representation. In this theorem, we have an equation like that if we have some number n, we can represent that number into this form: ak multiplied with b raised power k, ak minus 1 multiplied with b raised power k minus 1, plus and so on, a1b plus a0. So this is one complete representation. So in this equation, b is an integer greater than 1, because if it is 1 raised power what, it would be 1. So it is something, b is a integer greater than 1, or you can, because it is a representation of integers, so you can consider it, because our first system is binary, it is starting with 2, so it is greater than 1. So b here you can consider it as a base. Okay, and then n, and here on the n is what? N is a positive integer. For example, if I will give you 750. And if I will ask, convert it into binary form like that, then so that n is 750 here in this. But this is one general equation for all the representations. So here a, k are the values which are multiplying with these numbers, and k is a positive integer, and from a0 to from this a0 to ak we have also the positive integers less than b and ak not equal to 0. So you have to just, so this is a representation. We can represent one integer into, by using this equation, into these forms. And you have, maybe you have seen this thing in your introduction of introduction to computers. Maybe this is a course in your first semester, first, second, introduction to computer or introduction to computing, fundamental something. Yeah. So there you have, maybe you have converted and calculated these whole series. With respect to this topic, we have, we can add two integers if they are given in the binary form, then you can say the series of bit strings. You can add these two, add these two additions, you can multiply them, you can divide, and you can take the remainders. That is the similar that you have done in your fundamental of computers or whatever. This one is a little bit different, modular exponentiation. So if you have two binary strings, you know that you can add their digits one by one, and if there is a carry, you can transfer that carry to the next one. So adding pairs of binary digits and moving their carries, this is simple. And for multiplication, if AB are two n-bit integers, then you have to multiply this A with the all. For example, here A, B0, here the binary system 2 raised power 0, 2 raised power 1, whatever. This is just a representation. A multiplied B0, 20, and this is the whole, you can consider it bit strings. You can consider them bit strings. A into this B020, you can consider them bit strings, and then you have to multiply this A into with the first, then plus A with the second, plus, and then A with the last, and so on. And then you have to sum it up. So this is the procedure for the multiplication of n bit integers. And similarly for division and mod. For division, if you have two integers A and B, A and D is positive, then Q is equal to A division B. What it means? We are dividing this A with this D, and you are getting the quotient. When you divide, you will get quotient. And when you will, and A mod D, when you divide A with D, and due to this mod, you will get remainder in this R. This is called mod. These are the just basic fundamental concepts that you already know about the integers or different number systems which are existing. Now, modular exponential. Modular exponential. For example, if you have to calculate b raised power n mod m. So this b raised power n, this is called exponential. N is the exponent, you know that. N is the exponent of this b. And you have the mod, concept of mod is there, so that's why modular exponential. Here we have to assume that this b raised power n is a very much large number. very much large number. And when it is very much large number, if I say triple nine, triple nine, triple nine, raised power, triple nine, triple nine, triple nine, and if I say mod 5, then it would be issue for you to solve that equation. Okay. This is, for example, what I'm saying. I'm saying, okay, I'm saying raised power, triple nine, triple nine, triple nine, triple nine, and then mod, maybe 3, then you will say, Khalli Walli. Okay. Then it will be an issue. So in these kinds of problems, now you will say that you will see that how we will solve these issues, these problems in an easy way. So modular exponential. So in cryptography is a field in which you normally encrypt something. For example, if you have a message, you don't want that your message should be read or understood by some person, then you will encrypt your message. Or you can say you will encode your message. And then you will send via the internet. And if somebody will get it, they will not be able to read that message because it is encrypted or encoded. And for that, you need some key. And by using that key, you can decrypt or then you can decode. So cryptography is that field in which you encrypt and decrypt something. So, so if you have to find b raised power n mod m, and you want to find it efficiently, when there is a word efficiently, it means within the less time. And then where b, n, and m are large integers. These are large integers. N, m, b, all are large integers. And if you will do with your simple arithmetic approach, so that would be impractical. That would be impractical to divide and again and get the remainder. So then what? Then we will use some algorithm. Then we will use some algorithm which will convert this into the binary exponent. For example, which will convert this n into the binary expansion, and then it will do something according to the statements given in this algorithm. So according to that algorithm, if this bn is given to us, we will convert this bn, we will convert this, especially this n, upper power, raised power, you can say, into a binary representation. So b and then a k minus 1 multiplied with 2 and then raised power k minus 1 plus and so on. A1 multiplied with 2, which means 2 raised power 1, and a0 dot 2 raised power 0, which is 1. So this is something which is a binary representation of this n. If something is written like that, you can further convert it into b a k minus 1. This is the same thing, a k minus 1, 2 k power, this is written here, multiplied with, next is what, b a k minus 2, 2 k minus 2, which would be here next, and then what, b raised power a1 dot 2. So this is an opened form, this is a short form, and this is an open form, so that you will understand. So that you will understand. You know that if 2 raised power 0 dot 2 raised power 1, or you can say if 2 raised power it is written, then you can write it as 2 plus 1. You can write. So that is that form. So this form and that form is only that, nothing else. Now, in the algorithm, procedure we are going to start, and the name of the algorithm is modular exponential. Here b is integer. Here it is, we have the b. B is integer, n is the binary representation with base 2. So the base 2 is written, which means 0, 1. You have to convert that n into the form of a bit string, into the form of 0, 1. And m is okay, positive integer. And what you have to do? You have to keep 1. You have to initialize x with 1. And then you have to initialize a variable power with b mod m. If b is given to you, then you have the m, divide that and keep the remainder here in this power. And after that, we have the loop for I is equal to 0 to k minus 1. For I is equal to 0 to k minus 1. What is k? The number of bits in it. Or I will give you the understanding when I will present some example. You will understand it completely. And then when I is equal to 0, when condition will be this, for example, if it is from 0 to 5, then it will first, the value of I would be 0, then it would 1, then it would 2. You can understand 3, 4, up to 5. If ai is equal to 1, now here ai is equal to 1. Here, this a is what? These are the bits of this binary form. And we are checking here ai is equal to 1. When I is equal to 0, a0, this bit. From the right hand side, we are starting. So in the bit string, we are checking if a0 is equal to 1, if that bit is 1, then do this thing. X is equal to x dot power. So whatever the value previously we have, x, and whatever the value power we have, multiply them. Whatever the result, divided with m, and whatever the remainder, keep it here. If this is 1, if this bit is not 1, if it is 0, then don't do anything here. Just execute that second statement, because that second statement is not with this if. This if and then is complete. And then, okay, if it is not 1, so this second statement will execute either it is 1 or 0. This second statement will execute. But if the value of this bit is 0, then this first will not execute, but second will execute. And it will do what? Whatever the value of the powers you have here or from the previous step, you have to calculate a square by multiplying it with itself. It is squaring. And then you have, whatever the result, you have to divide it with m. And then you will have to update that thing in that power. So in each step, you are calculating this power also. So this power is only for this first step. After that, you will have the changed power. And then when this loop will be ended, finally, you are returning that x value. Whatever the value in x, you are returning. And what is that x? S equals b raised power n mod m. Whatever you will have that in x, that would be equal to b raised power n mod m. That would be the result of our question. So according to that, so as far as the understanding of this algorithm, it's simple. No any statement is complex. Now we are executing this algorithm on this example. Use algorithm 1 to find 3 raised power 644 mod 645. What is b here? B raised power n mod m. So this 3 is b. B raised power n. This is n. And this is m. So this n, we have to represent this n, 644, into the form of a... Huh? I zoom it. Okay, that's maybe my Mac will do automatically. Because this is a feature of the Mac, not the feature of the PowerPoint, okay? If I will do like that, this is the feature of MacBook or iPhone, yeah. but I have to control it. Much better. Okay. So now this 3 is, where is my pen now? Just a minute. My pen is now gone. But let's see if I will do them like that. Okay. Maybe I have some options of this PowerPoint. I don't know. If I will use the pen, then these things will be. Is it okay? Yes. What I have done here? Allah. What I did previously, I don't know. So what I'm saying here, 3 is B, 644 is N, and this 645 is M, according to that previous equation. And now we have to find it using that algorithm which is given in the previous slide. So for that, we have to convert N, which is this one, into the form of a binary representation. And if you will start the binary representation, this first one is 1, this is the position of 2, 4, 8, 16, 32, 64, 128, 256, 512. 512 plus 128 plus this 4 would become 644. And the rest of bits are 0. Rest of the bits are 0. So first you have to convert. You can convert that decimal number into the binary number system using your already knowledge that you got from fundamentals of computers. That is not the part of this course. So after converting, now you can start your algorithm. What you have to do, you have to check, you know that x is equal to 1, okay, you assign x is equal to 1, power is equal to b mod m. What is b? Sorry. Here b is 3, m is 645. So what? 3 mod 65. 3 mod whatever it is, 6, whatever, 65. 45? 645. 645. How you divide it? What is the answer? How you divide it? Scientists, how you divide it? What is the rule here? This is the fundamental question of class 2 or 3. How you divide it? Anybody? This is what you will do. Okay. Here the remainder will be 3. You can multiply it with 0. That will multiply with 0, you will have 0 and then the 3. Anyhow, now everything will be clear. I can read it, but I want to make a shortcut, okay? So x is equal to 1. X is equal to 1 and now power is now 3. Power is what? 3 mod 645, that would be 3. And then what? For I is equal to 0. Now your loop will start with I is equal to 0. When I is equal to 0, now these steps are here. I have just copy pasted from the book. I is equal to 0. And now because now when I is equal to 0, we have A is equal to 0. Which bit we are checking? This one, A0. Because A is equal to 0, so then what? What is the statement? We are A is equal to 0. This A1, A is equal to 1. So this is not working now. Only this one will work. And what is that one? Squaring and then modding. So A is equal to 0. So we have, initially we have x is equal to 1 and power will become, previously it was 3. So squaring 3 square and mod 645. According to that statement in the algorithm. According to that, this is square. 3 multiplied by 3, 3 square. And mod m is 645. So it is what we have written here. So 9 mod 65, still it is small. So by using that approach, you have the 9 here. And now what will happen? Now I will go here and I is equal to 1 now. And when I is equal to 1, I am checking A1. A1 is again 0. So the first statement will not execute and the second statement of squaring will execute it. This squaring will execute. This first statement will not execute. So we have x is equal to 1 and power is equal to use this previous power value. 9 square, power multiplied with power. 9 square mod this one, it is 81. It is still small. So by using the same approach, we have the 81. Because 645 multiplied by 0, you will get 0 and the remainder is 81. And now I will become 2 in the algorithm. And that's when I will become 2, we are checking A2. So this one, A1. A2 is equal to now 1. When it is 1, now this statement will also execute. This statement will execute and this will also. Both statements will execute. So now A is equal to 1. Then what? X is equal to x multiplied by power. Mod m. X multiplied by power. Value of x is 1. So we have x is equal to 1. So that 1 is the value of the x previously that we have. And dot power. Power is what? 81 in the previous step. So 1.81 mod 645. Rashidi, understanding or not? Inshallah, everything will be okay. Okay. So we have x 1.81 mod 645. So okay, multiplied, it will become 81 multiplied by 1, 81. And so this is mod 65. It is still small, so it will be 81. And now execute the second statement in the algorithm. And that is power square mod m. So what is that power? So this is now This is the value for the x, not the power. So previously we have, what is the power previously? 81. So 81 square mod 65. So that would begin, that 81 square, that would become 6561. Now it is greater than this one. Divide it properly and you will have 111 as the remainder, which you will update in the power. So now your power is this 111. Your x is what? This one. And you can keep on going. It's the same steps. It's a same, huh? Yeah. Yeah. Calculate, because it is mathematics. Calculator is allowed. Similarly, when you are here, for example, here, x is equal to 471 in step 8, and power is equal to this one, 111. And when I is equal to 9, because a9 is again 1, so the last step, x dot power mod m. First step is x dot power mod m, and second step is power square mod m. So when a is equal to 9, which is 1, so x dot power. So previously x is 471, that is written here. X dot power, and power is what? 111. Write it here, mod m, and then you will have the value of the x as this one. So this last value of x, whatever you will get, you can calculate the next power also. It is not mentioned here. You can calculate the second step. But this is what the last step. Whatever the last value you will get for that x, that is the solution for this. So therefore, this 36 that you are getting is the solution of, is equal to 36. Is the result of this expression. And now these are the exercises that you have to do from this section 4.2. And inshallah, I will start from here in the next class. What is the time? If it is not too much, then I can continue.
3 minutes.
Okay. We have 7 minutes. Actual time is finished. But anyhow, I will start from here because now the section is ended, so it's not. We will start inshallah from